Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, good to go. And welcome back to my course, to my class. So we have done about the discussion on processor. And from now on, we'll start explaining the other parts of computer, which is memory. And actually, there are some kinds of memory. We have internal memory, we have external storage, also we have cache memory. We'll start discussion from cache memory first because this is the shortest one. Okay, so with cache memory, I'll explain maybe these three first section, okay, because the others one are machine specific. Okay. Let's see the key points. With the computer memory, it's organized into hierarchy. At the highest one, there are processor registers. Next comes one or more levels of cache, and when multiple levels are used, then they are denoted as L1, L2, and so on. Next comes main memory, and all of these are considered internal to the computer system. And the hierarchy continues with the external memory, sometimes called external storage too. And next level typically being a fixed hard disk, and one or more levels below that consists of removable media such as optical disc and tape. Maybe for optical disc and tape, it's not longer commonly used now, but it is in past common. Okay. And as one goes down the memory hierarchy, one finds decreasing cost bit, increasing capacity, and slower access time. Okay, and it will be nice if you use only the fastest memory, but because it is the most expensive memory, that we have to trade off excess time for cost by using more of the slower memory. Okay, and this is the true challenge. Okay, then let's see the computer memory system overview. Okay, so let's see this table 4.1, the key characteristics of computer memory system. Okay, so the term location in this table, it refers to whether memory is internal or external to the computer. So internal memory is often equated with main memory, but because actually there are other forms of internal memory too, that we actually need to distinguish this term. Yeah? And the processor requires its own local memory in the form of registers. Okay? And further, we shall see that we control unit processor may also require its own internal memory. Okay. Cache is also another form of internal memory which will be discussed in this lesson. Okay. So we have this, okay, see, location. Also the capacity differs, the unit of transit differs, access matters also differs for types of memory. The performance also outlined by the access time, cycle time, transfer rate. This is the summary. So obvious characteristic of memory is capacity. Okay, this is the second one. Okay, capacity. So for internal memory, then this is typically expressed in terms of bytes. Okay, where one byte equals 8 bits, or sometimes it can be expressed by words. Okay, but actually there are no only one definition of word. Okay, because actually we have discussed about word right from before. Okay, when we're dealing with processors thing. Okay, so actual word length is actually very dependent on the machine that we are discussing about. There's sometimes 8, there's sometimes 16, and there's sometimes equals to 32 bits. Okay, so external memory capacity is typically expressed in terms of bytes. And a relative concept too is the unit of transfer. Okay, for internal memory, then the unit of transfer is equal to the number of electrical lines into and out of the memory. Actually, this is called the bus. Okay, and this is equal to the word length, but it's often larger. Okay, sometimes. Okay, and to clarify this point, okay, so you need to really understand these three things. Word, what is the natural unit of the organization of memory, and the size is typically equal to the number of bits used to represent integer and the instruction length. But actually, there are also many exceptions here. Second is addressable units. Okay, in some system that this is the word, but many systems also allow addressing at the byte level. The third one, it is unit of transfer. For main memory, that this is the number of bits read out of or written into the memory at a time. And this unit of transfer didn't equal a word or an addressable units. For external memory, the data are often transferred in much larger units than a word, and it's called a block. Also, another distinction is what called method of accessing. There are some types too. First one is sequential access. Okay, so memory is organized into units of data, which is called records, and access must be read into a specific linear sequence. Okay, the start addressing information is used to separate records and assist the retrieval process. Okay, second one is direct access. Okay, so with sequential access and direct access also involves share read-write mechanism. Okay, share read-write mechanism. Okay. However, that the individual blocks or records have a unique address based on the physical location. And access in this case is accomplished by the direct access to reach a general vicinity plus the sequential searching, counting, or waiting to reach the final location. The third type is random access. Then each addressable location in memory has a unique, physically wired-in addressing mechanism. And time to access is independent of the sequence of prior access and is always constant. And any location will be selected at random and directly addressed in access. Okay. Associative. Okay, associative. This is a random access type of memory that enables us to make a comparison of desired bit location with a word for a specific match, and it is for all words simultaneously. The next consideration is from the performance. There are three parameters. The first one is access time or latency, okay, which is the time it takes to perform a read or write operation. Okay. The second one is memory cycle time. Okay, and this is mostly applied to RAM and consists of the access time plus any additional time required before a second access can commence. The third one is transfer rate, and this is the rate at which the data can be transferred into or out of a memory unit, and this equals 1 over cycle time. And the relationship is shown by the equation 4.1. A variety of physical types of memory also have been employed. Okay, the most common ones are semiconductor memory, magnetic surface memory, used for disk and tape, and optical and magneto-optical. Also, several physical characteristics of data storage are important. Okay, in a volatile memory, then information decay naturally or lost when the electronic power is cut off or switched off. But with non-volatile memory, then the information once recorded remains without deterioration until it is deliberately changed, even when no electrical powers. So the information will always be retained. Okay. Then after this, let's see the memory hierarchy. Okay. So actually, a variety of technologies are used to implement memory system, and across this spectrum of technologies, then there are some relationships that hold. The first one is that faster access time, that is greater cost per bit. The second is that for greater capacity, then the smaller cost per bit. The third one is that the greater capacity, then the slower the access time. So here's the dilemma. Here are the dilemmas that are faced by the design. Okay, The design authors want to make a memory that provide large capacity because capacity is needed and also the cost per bit is low. But to meet the performance requirement, they also need to use expensive, relatively lower capacity with short access time. And here we come with memory hierarchy. Okay, the hierarchy is depicted in figure 4.1 as shown as in this pyramid. Okay, so as one goes down the hierarchy, then the following things occur. First, the cost per bit decreases. Second, the capacity increase. The third is that the access time increase, and the fourth one is that the frequency of access of the memory by the processor decreases. Thus, smaller, more expensive faster memory are supplemented by larger, cheaper, slower memory. Yeah, actually, there's quite many things. Okay, let's go into here. So the three forms of memory just described are typically what the three forms of memory. Uh, hmm, yeah, this one. Okay, register internal to processor, main memory of system computer. This is the one that uh, is described here. Okay, so they are typically volatile and employ semiconductor technology. And the use of three levels exploits the fact that semiconductor memory comes in a variety of types which differ in speed and also cost. Okay, the external non-volatile memory is also referred to secondary memory or auxiliary memory, and this is also used to provide an extension to main memory, which is called virtual memory. Okay, now let's go into case memory principles explanation. Okay, so there are some important things here. Okay, so cache memory is intended to give memory speed approaching that of the fastest memory available, and at the same time provide a large memory size at the price of less expensive types of the semiconductor memory. So here shows a single case structure, the CPU, case, main memory. Here we have word transfer, which is fast, and here we have the block transfer, which is slow. And it's three-level case organization, which has the L1 case, L2 case, L3 case, fastest, fast, less fast, slow. Okay, so the case actually contains a copy or portion of main memory, and when the processor attempts to read a word or memory, a check is made to determine if the word is already in the cache, and if so, then the word is delivered to the processor. If not, the block of main memory consists of the some fixed number of words is read into the cache, and then the word is delivered through the processor. Okay, and we also see from this that L1 is fastest, L2 communication fast, L3 become less fast. Okay, so the L3 case is the slowest one, and L1 is the fastest one in the case of three-level case organization. Okay, so main memory consists of up to two to the n addressable words, and with each word having a unique n bit address. And for mathematical purposes, then this memory is considered to consist of a number of fixed length block of k words each, and this is called lines. Okay. The length of line, not including tag and control bit, is called the line size, and the line size may be as small as 32 bits. Okay, and number of lines is considerably less than the number of memory blocks, and any time that some subset of the block of memory resides in lines in the cache. Right? Because there are more blocks than lines, and if an individual line cannot be uniquely and permanently dedicated to a particular block, and thus we have what called a tag. Okay, that identifies. Okay, so we have tag that identifies which particular block is currently being stored. Okay, let's see the operation by this flowchart. So this is cache read operation. Okay, I want you to understand. To evaluate this flowchart by yourself. And this is how the typical cache organization be done. Okay, so you see, the cache connects to the processor in this chart. In this figure, via data control, and address lines. And the data and address lines, address data, also attach to data and address buffer, which attach to the system bus from which the main memory is rich. And when a case hit occurs, then the data and address buffers are disabled, and communication is only between processor and cache with no system bus traffic. And when a case miss occurs, then the desired address is loaded onto the system bus, and the data are returned through the data buffer to both the case and the processor. Now let's see the elements of cache design. Okay, we have case addresses, cache size, mapping function, replacement algorithm, write policy, line size, and number of caches. We start from case address. So, in essence, that virtual memory is a facility that allows a program to address memory from a logical point of view without regard to the amount of main memory physically available. And when virtual memory is used, then the address field of machine instruction contains virtual address. Okay, then we have what called a hardware MMU to translate each virtual address into a physical address in main memory. This is very important. That's why we make it red here. Okay. When virtual addresses are used, then the system designer may choose to place a cache between the processor and the MMU or between the MMU and the main memory. Let's see the figure. Okay, so you see the cache between the MMU or between the MMU and the main memory. Okay, you see, this is two kind. Okay, so one obvious advantage of the logical cache. Okay, so the first one outlines the logical cache structure, and the second one is outline the physical cache structure. Is that case in logical cache, access speed is faster than physical cache because the cache can respond before the MU performs. Okay? Perform an address translation, but there are also the disadvantage. Okay, it has to do with the fact that most virtual memory systems supply each application with the same virtual memory address space. Okay, and thus the same virtual address in two different applications refers to two different physical address. Okay, and therefore this must be completely flush with each application context switch, and extra bits must be added to identify which virtual address space this address refers to. And for the case size, see, the larger the case, and the larger the number of gates involved in addressing the case. And the result is that larger cases tend to be slightly slower than a smaller one, and even when built with the same integrated circuit technology and put in the same place of chip and circuit board. Then we have mapping function. We have some kind. There are three techniques that can be used, which are direct, associative, and set associative. Let's see one by one. This is quite mathematical. I'll explain one by one. Direct mapping is the simplest one, okay, which maps each block of main memory into only one possible cache line. This is expressed as shown. Okay. Second one, this is the direct mapping technique is simple and inexpensive to implement. This is the advantage. Okay, very clear. But also the disadvantage is that there is a fixed cache location for any given block, and so a program happens to reference word repeatedly from two different blocks that map into the same line. Then the blocks will be continuously swept in the cache, and then the hit ratio will be low, or called the thrashing. And one approach to lower this kind of penalty is to remember what has been discarded in case it is needed again. Okay, and since this has already been fetched, it can be used again at just small cost. Okay, so there's the thing. In such recital is possible using a victim case. What is victim case? Okay, is actually proposed as an approach to reduce the conflict misses of direct map cases without affecting its access time. Okay, then we have associative mapping. Okay, which overcome the disadvantage of direct mapping by permitting each main memory block to be loaded into any line of the cache. Okay, and there we have what called tag and word field. And tag field is uniquely identifies a block of main memory. Okay, and yeah, you see here with associative mapping, then there is flexibility as to which block is replaced when a new block is read into the cache. And the replacement algorithm introduced to this to maximize the hit ratio in this kind of mapping. And also, this third one is set associative mapping. So this is a compromise that exhibits the strength of both the direct and associative approaches while reducing your disadvantage. The relationship is this, and also the set associative mapping is also called the k-way set associative mapping. Okay, for the set associative mapping, then the case control logic interprets a memory address as trivial. They are tag, set, and word. Okay. Yeah, it's actually full of figures of examples, but maybe I'm not going to a very great deal of explanation. Yeah, and just make it short. Yeah, maybe for replacement algorithms, it's next time. Yeah, maybe I want to share to you a quote for today. It's by George Adair. So everything you have ever wanted is on the other side of you. And that's for our lesson today. I'll continue on the next day. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https://science with xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.